Hello everyone, welcome to this video. In this video, we're going to talk about the normal distribution, and to be very specific, we're going to get the intuition for the equation of the probability density function, the PDF of the normal distribution. So if we come down and see here, if I zoom in a bit, we'll be able to see this is the very equation for the probability density function, the PDF of the normal distribution. So if you are, very comfortable with normal distributions, if you have worked with it, you are very well known with this equation. So in this video, what we're going to do is we're going to give a intuition of how this equation came about and how every small component of this equation has an impact on the famous bell-shaped curve of the normal distribution. So what we're going to do is essentially the agenda will be to achieve the bell-shaped curve, and in the process, we'll be able to see using the first principle approach as we will be building everything from scratch and we will be able to achieve the normal distribution's bell-shaped curve. And in that process, we'll be able to realize what impact or how every small component of this equation affects that curve. So yeah, let's do it using a visualization tool called as Desmos. So this is the Desmos page, as you can see. It's a very easy to use tool. So if you have seen the bell-shaped curve, if I move back to the Wikipedia page and show you the bell-shaped curve over here, you'll be able to see this is the bell-shaped curve. So we are to build this curve as an end goal. So let's move back. So we have seen this bell-shaped curve has two components, one exponential increase and an exponential decay. But both of those are combined together at a peak and they form a bell-shaped curve as a result. So if I were to see the exponential increase, it's nothing but e to the power x, and it gives us the exponential increase curve. And simply by adding a negative sign over here, it will give us, and sorry, the negative sign should be at the exponent part. If it's negative x, it will give us an exponential decay curve. But I need to combine both of them and attain that bell-shaped thing. So for that, we just simply need to add an exponent of square to the x. So see, we will be able to see how beautifully we're able to achieve the bell-shaped curve of the normal distribution. And also the actual equation has a half before this x square in the exponent, for standardization of the variance purposes. So this is the very simple equation of e to the power minus half x square, and it already gives us, the bell-shaped curve that we can see for normal distribution. So you must be wondering, if I have this curve simply with this simple equation, why in the world would I need to have all those parameters like mu, sigma, and the 1 by root over 2 pi sigma square? Uh, aren't those unnecessary? But while we will be understanding this video, the significance that each of this component has. So what essentially the problem here with this graph is, this is obviously a normal distribution bell-shaped curve. It has all the properties of the bell-shaped curve. But the thing is, this is, fixed at its position, and also its shape. You cannot change it by changing anything in this equation. So we need something to be able to control two things in this graph. One, the position of this graph, we want to move it along the x-axis to different positions. And the second, we want to control the shape of this curve to make it more flat or more spiky, obviously while maintaining the bell-shaped properties. And for doing these two things, we need two parameters of the normal distribution. And so let's go step by step. If I want to move it along the x-axis, what I simply need to do is add, I need to add a parenthesis over here. I need to subtract the mean of the population from x. So if I simply add m, which signifies the mean over here, and add a slider for it, I'll be already able to see that when the mean is 1, the curve has shifted with its peak over 1. You can see here, the peak is over 1 instead of 0, which was previously. And if I simply move the slider, if you observe carefully, the graph beautifully moves along the x-axis while I change the value of m. And this is how beautifully, by introducing this x minus m in this equation, we're able to move this bell-shaped curve along the x-axis to any location of our choice. So this mean is one of the parameters of the normal distribution, and this it basically controls the location of the curve. And so, yeah, we're able to achieve the one thing of the two things that I have spoken about. The next thing is we want to control the shape of this curve to be more spiky or more flat. And in order to be able to do that, what I need to do is I add one more parenthesis to this, uh, and then I divide it by the standard deviation, which I signify here with S, uh, which is sigma in the actual equation, which is nothing but a standard deviation of the population. So if I add it and add a slider over here, now if I change the value for S as preset is 1, so the standard deviation is 1. And if I change the standard deviation to any different value, if I increase it, for instance, the dispersion of the graph or the spread of the graph is increasing, as you will be able to see, and it becomes more and more flat and flatter. And if I decrease it from 1, you will be able to see the graph becomes more and more spiky. It becomes more and more spiky. And negative doesn't make any sense because the standard deviation is nothing but square root of the average of squared distances of every point from the mean, and that's variance, and then you square root that to achieve the standard deviation. So that would never be negative. So negative doesn't make any sense here. Let's ignore it. And if I go just to 0.3 and 0.2, it becomes more and more spiky, and if I increase it, it becomes more and more flat. And that is exactly how we're able to control the shape of this bell-shaped curve while maintaining the bell-shaped symmetricity of the bell-shaped curve, while making it more spiky or more spread, basically controlling the spread of the curve. So this is the second parameter that controls the spread of the curve. The first controls the mean, it controls the location, and the standard deviation controls the spread of the curve. So yeah, these are the two parameters. And if I, say, change it to the initial setting of standard deviation to be 1 and the mean to be 0, what I'm actually obtaining over here is the something that I had initially obtained, before introducing the parameters of mean and standard deviation. And this is actually the standard normal distribution curve. And when mean is exactly equal to 0 and the standard deviation is exactly equal to 1, the curve that you see is the standard normal distribution. And it's a very, important curve because this is used as the standard reference for getting the z-score values using the z-score tables and making many different calculations. So yeah, so we have this equation, which is basically the right half of the equation. And we already have our beautiful bell-shaped curve, and we have understood it. So the main question now arises is, why in the world would I have this coefficient of 1 by root over 2 pi and sigma square? So that could be understood by a very simple explanation. If I were to give in very brief, is that when we, integrate this equation of the PDF from minus infinity to plus infinity, that basically we know in calculus gives us the area under the curve, and the area under this probability density function should be equal to 1, and that's a property because the total probability is equals to 1. So the area under the curve needs to be 1, and by chance, when you integrate this half of the equation that we have built already, you get some values which is not exactly equal to 1. And to be able to cancel it out and bring that value to 1, we had to introduce this coefficient of 1 by root over 2 pi sigma square, so that it cancel it out and gives us a net value of 1 for the integration from minus infinity to infinity for this PDF curve. So yeah, that's the entire thing. If you want, I could just put in the 1 by square root of 2 pi, and then the outside we have the s. If I put it, the graph is still the beautiful bell-shaped curve, as you can see. And this is the actual curve with the entire equation put in place. So yeah, that's all. We now understand every small component of this equation and why they exist and why they are important. So yeah, that's all for this video. Follow for more.